So from the scalability perspective, you have this piece of computation, and if your network consists of heterogeneous devices, which it does, and this is the case even if you have some sort of ideal consensus mechanism underlying your ledger, because you have to at least perform the computation to check whether it's valid or not. Right? Okay, so there's a scalability issue. There's also a privacy issue, right? So if I publish this computation, for people to execute it, they need to be able to know what the program is, what the input is, etc. So what happens in practice is that when I publish this transaction, people can see what the executed program is, what the input data to the program is, and finally who invoked the program, right? And this information is stored on the ledger for all eternity. As long as your blockchain is around, people can see this information. So this is bad. So what we try to do in ZEXE is construct a system for performing these computations offline, and then you can publish transactions attesting to the correctness of these computations to your ledger, and people can verify these transactions. And what we get in terms of properties is that we have some sort of ideal privacy, in that the transaction reveals no information about the input program or the data or who invoked it. All that stuff is hidden. So we have a good notion of privacy. We get succinctness, so concretely the proofs are constant size. In our implementation, we get like around 1 kilobyte transaction sizes, and verification is less than 50 milliseconds, which is quite good. And this is all independent of whatever computation you're performing. So even if it's a massive computation, your verification is still constant size and the proof is constant size. Okay, that's great. So how do we fare in terms of functionality? Right? What we get in ZEXE is arbitrary user-defined functions. I can execute whatever computation I want in the system, while still isolating malicious functions from honest ones. So if you have some sort of evil function in your system, it can't screw up the execution of honest functions. But what we still allow is for these functions to communicate with each other. So you can have inter-application communication and interaction. Okay. So it's not just some pie-in-the-sky theoretical system. We use it to, we show in the paper how to construct these, a couple of different applications. We show how to construct private user-defined assets, private stablecoins, which have like different sorts of policies around transactions, and also how to trade these different kinds of assets via private, decentralized, or non-custodial exchanges. Okay, so that's the summary of ZEXE. In this talk, I won't talk about ZEXE in its full generality, but instead I'll focus on how you can take ideas from ZEXE to construct a couple of the applications I talked about in the previous slide. Namely, I'll show how to construct these private user-defined assets and private decentralized exchanges to trade these assets. Okay, so why these two applications, right? Well, arguably, it's the case that user-defined assets like tokens are the most successful application, or most popular application of smart contract systems today. So if you can support this application, you're also supporting a large majority of the use case of modern systems, of modern smart contract systems. So that's +1 there. But also, there's also many different kinds of tokens that people try to construct and trade, and these have, like for example, in Ethereum, you have these ERC20 tokens, 721 tokens, you have stable coins, and these have different sorts of issuing authorities and different sorts of transaction policies. So all kinds of different stuff is going on. So if you have a system which supports this very large array of functionality, that is an exercise of its functionality properties or expressivity properties. Right? So you can support that, and that's another +1 for ZEXE. Okay. So let's say you have a system that supports these things. Now, the most popular thing that people want to do with these tokens is to trade them, right? So the question is, how do you trade these assets? And today, there's a couple of different mechanisms that are popular. So the most popular is these centralized exchanges. And what happens in these is that the user, when they want to trade, they give up custody of their assets to the exchange, which then basically performs the trade on their behalf. So this is, giving up custody is obviously not a positive thing, right? This has led to a lot of problems for the community in terms of loss of funds for users due to fraud on the part of the exchange, just security breaches, or just plain human error. So ideally, we'd like to avoid this. So, okay, let's keep that in mind. But okay, for this downside, there's also a lot of benefits of these centralized exchanges. The first is that you get nice efficiency properties. So because, the exchange controls the assets. Whenever two users using the same exchange make a trade, the exchange just has to update some records in the database. There doesn't have to be any on-chain activity. So you don't incur the latency of your ledger or your blockchain to perform a trade. So that's a plus one. They also offer some notion of privacy in that now it's only the exchange that learns the details of the trade. Because, as I said, if you're just updating entries in a database, most of the information doesn't really go to the ledger. So you have that per user trade information is hidden. Okay, so that's some nice properties of these exchanges, but this giving up custody is a real negative, and to solve this, people have tried to come up with so-called decentralized or non-custodial exchanges. And what happens in these is that the user retains custody of their assets throughout the trading process. At no point does the user give up custody to any third party during the trading process. Right? So this is obviously very nice, but with this property comes a couple of downsides. So this leads to inefficiency because now every trade requires an on-chain transaction. So now every trade requires the latency of your ledger to confirm the transaction. And if you're using these non-private smart contract systems like Ethereum, you also lose all notions of privacy because every observer can see the details of your trade, like who are the participants in the trade, what is the value, what are the assets, et cetera, right? Okay, so let's see how we can solve. So in this talk, I'll focus mostly on solving the privacy downside of these decentralized exchanges or DEXs. I think you can, I don't know, this complementary work like Ellie's talk earlier demonstrated on getting scalability or more efficiency for these non-custodial exchanges. Okay, so privacy. So as I said, every trade goes on the ledger, right? And the transactions, it reveals the participating parties, which assets are involved, as well as the values of these assets. And this has itself two downsides, right? So from the user's perspective, their financial privacy is completely compromised because the trading history of the users is now public on the ledger, and so now you lose fungibility, which I don't think I need to explain to this audience. But also, if I don't know, you have some very super secret trading algorithm that you want to keep secret, if people can observe your trading patterns, then your algorithm is no longer super secret and you lose your business advantage. So you want to keep that private as well. Okay, so that's from the user's perspective. But this lack of privacy also has some sort of global downside for the ecosystem in that you get this problem of front running. And what this means is that, for example, let's say you're a miner on the network, you see this big order coming in, and you know that the price is going to change because of this big order. What you do is you publish your own transaction that takes advantage of the existing prices. And now when the prices later change, you can go in and profit off of this price change. And this is just one example of front running. There's lots of variants that allow you to do different kinds of things. And this is not just some sort of theoretical concern. There's been some nice line of work from the folks at IC3 which show how you can exploit this kind of information to actually make a significant amount of money doing front running. And one particularly cool attack is that this front running actually compromises security of your entire blockchain. They call it like a time traveling attack. Super cool, you should check it out. Okay, so lack of privacy causes a bunch of problems in this DEX ecosystem, right? So let's see how we can fix that by first constructing private user-defined assets and then showing how we can trade them using private DEXs. Okay, so let's get started. So our building point will be the zero-cash paradigm because ZEXE really builds off of the zero-cash protocol, and also because it's really the only fully anonymous or fully private decentralized payment mechanism that we know of, right? Okay, so what happens in zero-cash is that you have a transaction consumes old coins and creates new coins, and the idea is that the sender, receiver, and value are all hidden within the same transaction, right? Okay, so you have a bunch of transactions on your ledger, and the idea is that there is no way to link the transaction that creates a coin and the transaction that spends it. So this link between the CMB and SN5 is hidden. And what Zcash also guarantees is that in this process of hiding, you don't lose integrity, which means that the value is conserved. There's no hidden inflation happening in the network, right? Okay, so that's nice. What sort of anonymity guarantee are you getting? So basically, your anonymity set for creating a transaction is a set of all prior coin commitments ever created, right? So you have this set of coin commitments, And you have a set of also consumed coins. And the point is that whenever you add a new serial number to a consumed coin to this set of consumed coins, there's no way to figure out which commitment it came from. So this link is completely hidden. All right, so you get some sort of nice ideal privacy guarantee, which is the anonymity set is a set of all possible coins ever created in the past. Okay. Yes, that are not controlled by the attacker. Sure, if your attacker is everybody but you, then you're screwed anyways. Yeah, good point. Okay, so that's the high-level description. Let's dive a little bit more into detail. This hopefully should be not too new to this audience, but I'll go over it in high level as well. Okay, so your transaction now consists of the serial numbers for the coins that have been spent and commitments for the new coins, and the idea is that these serial numbers should not be repeated. So if you see the serial number twice, then you know that the coin is being double spent, and so you just reject that transaction, right? And to get some, but this is not enough. What you want to prove is some properties surrounding these old and new coins. And this is achieved via a zero-knowledge proof that's included in the transaction, right? And what this proof attests to is that, first, that the coin that you're spending actually exists, that it's not coming out of thin air, that it belongs to it was created in some transaction in the past. And technically, this is done via the proof of membership in the commitment Merkle tree. So your transaction also includes this Merkle tree root. Okay, so you prove that your old coins exist. You prove that the coins that you're spending are not double spent, and this is done by making sure that serial numbers are generated correctly. So that's the old coin stuff. And finally, you want to ensure that the new coins are created correctly as well. So the new coin commitments are so-called well-formed. And this is again checked by, so you have your coins, which consist of the public key, the value, and this row thingy. Ignore the row. And the point is that these commitments must correspond to these PK, V, and row. Okay, so that's three things. The part that we're concerned about in this talk mostly is this last part about the conservation of value. So if you want integrity, you want that to not be hidden in inflation. And what the proof achieves this by ensuring that the old coins, the value of the old coins is equal to the value of the new coins that you're creating in the transaction. They're not making money out of thin air. There's also like a rain check there, but the high level idea is that you want the value to be conserved. Right, okay, good so far. All right, so that's zero cash. And as I said, zero cash achieves ideal anonymity for a single asset on a single blockchain. How can you take that further and try to achieve ideal privacy for multiple assets that are possibly user-defined on the same blockchain, right? Okay, so one way to do that would be to just, like say you have asset A and asset B, you run independent instances of zero cash, of the zero cash protocol for asset A and asset B. So you have zero cash A and zero cash B. But this is not quite satisfactory because the problem that you have is your anonymity sets are now partitioned. Like zero cash A has a different anonymity set from zero cash B. And if zero cash B has only like 10 users, as Dara pointed out, then you don't really have any anonymity at all, right? So what you want, in some sense, is to have some sort of combined anonymity pool across all the assets in the system. So let's see how we can do this. So you can so we have basically the same structure as before. We have all the infrastructure surrounding the Merkle trees and the serial numbers, all that is preserved. But what we change is that last point about value conservation. So what we do is we take our coins, and now we store in the coins not only the value, but also some sort of asset identifier. So you have your coin now stores this pair, ID and V. And what you check inside the proof is that for every asset in the transaction, the value of that asset should be conserved. So if you have asset A and asset B in the same transaction, then respectively asset A and asset B's values should be conserved. And there's a little bit of a footnote about generating the IDs, or how you generate this securely. See the paper, it's a bit of a technical detail. Okay, so the idea now is that because the proof hides information, and the commitments and the proof together hide information about the identifier or the asset identifier, and the transaction as a whole doesn't reveal any information that now you're having transactions for asset A and asset B at the same time. So now all the assets share the same anonymity pool, right? Okay. So that's nice. So now we have these multiple user-defined assets, completely private, on the same blockchain with the same anonymity pool. But they're still isolated in some sense. And this means is that there's no interaction between the different assets. All you're doing is you can put them in the same transaction, but they can't really interact in any way. So how do you enable applications that interact with multiple assets? In particular, how do you do stuff like trading, where you do have to, I don't know, have some interaction between the two different tokens? Okay, so what we can do is, so now we have, again, the same structure, but now we store even more information inside our coin. So we have your ID and V and all that stuff. We store some additional arbitrary auxiliary information. And so you also, now you check that the value is conserved. But what you do now additionally is you associate your coin with a so-called death predicate. And what this predicate says is that when I spend a coin, I have to ensure that the predicate is satisfied. And this predicate can be any arbitrary computation. So anything, any arithmetic circuit, you can put that in there. And the proof will assert that if you're spending a coin, then the predicate for that coin must be satisfied. Okay? And this is only for the coins that you're spending in the transaction for the moment. We don't care about the predicates of the new coins being satisfied right now. Okay, so let's see like what we can do with this. Okay, so let's just recap in terms of privacy guarantee. What we get is that the transaction reveals absolutely no information about this IDV, all that stuff. So it hides information of the coins, but it also hides information about the computation that's occurring. Right, the proof is zero knowledge, so you hide that last part, like what is the phi of each coin, and like if it's satisfied or not, or like which phi is satisfied. So the transaction reveals no information about anything, basically. So all you see is this opaque serial number, commitment, and proof, and nothing else. Okay, so let's see how we can use these predicates in an application. And specifically, I'll show how to do private atomic swaps. And why atomic swaps? Because they're a key component of constructing these DEXEs, at least in our paper. Anyways, so let's say you have this coin that you want to exchange for some other coin, right? So it has the public key, it has the ID, V, and some auxiliary information. And since you want to do this exchange, you associate it with this exchange death predicate. So you can see the phi old is equal to phi exchange. We'll see what that is in a second. So what I want to say for this coin is that this can only be spent if it's part of a transaction with, say, another coin of asset type B, specifically. How I do this is by what I do inside my exchange death predicate is I look inside this auxiliary information for my C1 old. I see, okay. And what I pull out is three pieces of information. I pull out this ID star and V star, which specify like what the identifier and value of the other coin in the transaction must be. So like what coin I want in exchange and what value I want in exchange. So that's what I specify inside the auxiliary information. I also identify like what address I want my coin to go to. The new coin I want, what address it should go to. Right, so I pull that out of the auxiliary information. I check that the other coin in the transaction actually matches this information, right? That the other coin actually has the correct ID star and V star, so it's the correct coin to exchange for. And then I perform the swap, so I make sure that the new coins that I'm creating in the transaction actually have the swapped values and identifiers, and that they're going to the right addresses. So the C2 goes to the address of C2 old, and C1 new goes to PK star. Okay, does this make sense? Okay. So if you have any questions, this is like probably the most technical slide in the talk. Okay, maybe you're good for now. All right, so for our DEX, now we have this key primitive of the atomic swap. But there's like a lot of other components as well, right? You want to be able to create orders in your DEX. You want to be able to discover that somebody has, I don't know, placed an order, and you want to be able to finalize the trade once you've done all these things. So let's see how we can do each of these steps. And we roughly follow a couple of existing paradigms in the DEX literature, or not literature, I guess, world. And there's two main frameworks, I think. So there's order-based DEXs. And the idea here is that there's an order book which maintains a list of orders that are published by makers. So makers are the people who bring the liquidity to the trade. And an order here is like the asset pair and the value of each asset in the trade. So your taker, the person who's completing the order, can come and look at the order book and see which orders are open and try to fill them. And examples of these include radar relay and IDEX and 0x-based protocols in general. Okay, another paradigm is so-called index-based relays. And the idea here is that now you don't have an order book, but you have an index instead. And what an index stores is intentions to trade. These intentions are now similar to orders, but they exclude the prices involved. So your public-facing ledger of orders or whatever doesn't have any price information, right? So you only have the intention that I want to trade A for B. The maker publishes his intention to trade. The taker can scan the order for these intentions, scan the index for these intentions, and then interact with the makers to fill out these orders. And an example of this is the swap protocol. Okay, so in this talk, I'll mostly be focusing on how to construct these index-based exchanges. Okay. So in an index-based exchange, you have your sell and buy. So this is like what an intention to trade looks like. A maker can come along, publish an intention like, I want to trade asset A for asset B, and this is my encryption public key. Please contact me there. A taker can come along, see this. Oh, I want to fill this intention. They interact using the encryption public key, and at the end, the taker produces a transaction which they can put on the ledger. And the idea now is that in terms of privacy, what you get is that because you're using some sort of non-private ledger, as we saw, your transaction reveals information about the maker and the taker, about the values involved and the assets, about A and B, and what the values VA and VB are, right? And this causes all the problems about user financial privacy and front-running and all the bad things that we saw before. Okay, so let's see how we can, what the paradigm for this intent or private version of this would be. So we have our maker who, as before, publishes this intention to trade. The taker sees this, interacts, and at the end now, the difference is that, so they agree on the terms of the trade, blah, blah, blah. And the point is that now they want to publish some sort of encrypted transaction in our system. So what our maker does is they create this coin A1 with asset A, VA, blah, blah, and fill out the maker's information in there. The taker's information there. So they put in the auxiliary information, B, VB, and their own PKM is overloaded. Never mind. Okay, so the maker creates this coin, sends over the coin along with the secret key used to spend the coin to the taker. The taker has, let's say they have the coin that can fulfill the terms of the trade. The taker can then publish this sort of encrypted transaction and publish it to the ledger. And what we get are these two trade anonymity and trade confidentiality properties. Anonymity says that you hide all information about the maker and the taker. And confidentiality says you don't reveal any information about the asset values and asset pairs involved. And these are useful. I don't think I have too much time, but roughly they're useful for separately hiding the transaction graph and preserving financial privacy. And the other one is useful for preventing front running, because now miners can see no information about the trade, so they can't front run because they don't know what to front run on. Okay, so that's basically wrapping up my talk. So we constructed these private user-defined assets. We showed how to get custom access via these predicates to these assets. You have some sort of scripting ability in private, right? And we showed how to use that to construct these private DEXEs. So what we do in ZEXE is basically you can take these ideas and stretch them a bit further, and then notice that you're not really talking about coins or financial stuff anymore. You can have arbitrary computation and arbitrary data, and then you have ZEXE. So to model this, we have some sort of formal modeling called a record nanokernel that describes how you do these computations. We show how to realize this with crypto, with our decentralized private computation primitive. And finally, we have an implementation that uses recursive snarks and efficient techniques from the sampling stuff, for example, to get some sort of efficient implementation that has reasonable proving times and verification times. Okay, so I'll take, this code is available on libzexe.org, and the paper is on that URL also. Thanks.
Thanks for a great talk. I have a question a bit outside of ZEXE. Is there any work on constructing this intent, like private intent-based exchanges with regard to scalability and privacy? Because the attacker could just query all the intents and
so one downside is that you could have, you could associate your index with some sort of querying fee or listing fee or something, so you could have some sort of deterrence mechanism there. But yeah, a taker could come along and query each maker and try to see if they have some actual liquidity and violate the privacy guarantees or for the maker. So that's definitely an attack. But that, I think, in some sense falls outside of the threat model, because now you need to have some sort of, I don't know, DOS or some sort of privacy guarantee on the index itself.
So I'm curious, is there any work on this? Is somebody doing? Or
Not that I'm aware of. I'm not sure. I haven't looked too deeply into the literature. So there might be.
Okay, cool.
Maybe using MPC or something. Thanks for the question.
Thanks for the talk. The predicates, what inputs do they need? What information about the transaction?
Oh, so they see, I should have mentioned this, but they see all the information about all the coins in the transaction. So they see the information about the input coins and the output coins, the values, the addresses, all that stuff. They get to look at that.
Okay.
And then make a decision based on that. So they're very powerful. You can implement, I don't know, time locks almost, and lots of functionality within the predicates.
Oh, I see. So they see information about where the transaction gets mined on the chain, so blocks.
So I mean, you would have to modify how you construct time locks, but it would be possible in a different way. We have to do like a retrospective thing, like, oh, this coin was created like 10 blocks ago.
Oh, right. Okay. Because when you're creating the transaction, you don't know where it should be mined.
Yeah.
Okay. Thanks.
Yeah. Thanks.
Pratyush, great talk. Thanks. I have kind of two questions. The first one is, when you use the ZEXE framework for kind of some things, what you described, right, private asset transfer or whatever, that is, let's say, kind of analogous to what sapling functionality has today, what's the kind of overhead that you get from using this kind of more generic framework? And the second question I'll just say is, when you describe the atomic swap, the private atomic swap, you describe basically doing kind of like a multi-transfer transaction in some sense, but then there needs to be some kind of agreement off-chain, right, between the two parties, so some communication. Yeah.
So that's what the intent or index was for. So basically, they communicate and then they agree on the terms of the trade. But we have in the paper a different protocol for where you don't need this sort of interaction potentially. But yeah. So to the first question, so going to this generic notion, we incur some cost because of we're going for very strong privacy guarantees, so we want to hide also which predicates are executing, but also because we're going for fully generic computation, and more than just payments, that's where I think we have to invoke recursion partially. So if you want to limit your expressivity or your privacy guarantee, then you can scale back and, so the key cost actually is because of the predicates, because of the recursion that's happening. If you sort of eliminate that, then you're maybe like looking at 2-3x overhead compared to sapling. Probably less if you optimize it better.
Thank you.
Yeah, thanks.
Thanks for the talk. Do I understand correctly that the main way to avoid front running is to make the maker and taker transact privately and agree privately on a trade? And if so, has there been done any research into how to allow public order books, public trades, but still prevent front running?
So there's this inherent like sort of tension between transparency and privacy, because if you have public order books and settlement on those order books on chain, how do you get privacy? We have so I talked about that order-based DEXEs as well. So we have in the paper construction of private order-based DEXEs, and then they have some loss in privacy guarantees and front-running, resistance against front-running because of this issue, because you list information about the trade on the ledger, on the order, for example. Sorry. So going to your question, I'm not sure. So maybe you can have some sort of MPC-based order book or something which tries to hide this information and then still get good privacy guarantees. But I don't know if how much work people have done